topic is Lagrange multipliers. So you have already read in your previous lecture about maxima and minima of the function of two variables. I will just recapitulate that. So what is maximum and minimum values? So you can see in this figure, this is the top of the hill and this is the again top of the hill, and these two, this point and this point, these are said to be the valleys, or the at these points function has the minimum value. Now in the next slide you can see what is absolute maximum. Now, as I have explained you in the previous slide, that here the function has the maximum value. So if you have the any point AB over here, so value of the function at this point is more than the value of the function at the neighboring point. Clear? Now again at this point, value of the function, say at any point a1 b1, is more than the value of the function at the nearby points. Now larger of these 2 points is said to be the absolute maximum. So this point is said to be absolute maximum, and this point is said to be the local maximum. Now what do you mean by a absolute minimum? So now you can see that at this point, value of the function at AB, if I have the point AB, is minimum as compared to the nearby points xy. Here again the value of the function at this point a1 b1, or you can say f of a1 b1, is minimum as compared to the nearby points. Now smaller of these two values is said to be the absolute minimum. So this point is said to be the absolute minimum and this point is said to be the local minimum. Now mathematically, how we will define the local maximum and local maximum value. So a function of two variables has a local maximum at AB if value of the function at that point is greater than is equal to value of the function at the nearby points where xy is near to AB. Now this means that f of xy, this is less than is equal to f of AB for all points xy in some disk with center at the point AB. The number f of AB is said to be the local maximum value. Now what is local minimum and local minimum value? So if the value of the function at any point AB is less than is equal to value of the function at the nearby points, then f has the local minimum value at the point AB. And f of AB, it is said to be the local minimum value. Now, what is absolute maximum and minimum? If the inequalities in definition 1, as explained in these two, holds for all points xy in the domain of f, then f has an absolute maximum or absolute minimum at the point A. Clear? Next, now with these inequalities, as explained in the previous slide, we can find the maximum value of the function, minimum value of the function. Now sometimes we have to extremize the function under some condition. So in those type of problems, we use the concept of Lagrange multiplier. I will explain you with the help of an example. So suppose I have the function fxy, which is equal to x square plus y square plus z square. Then what is the minimum of this function? So obviously minimum of this function will be 0 0 0, because x square plus y square plus z square, it is always a positive quantity. Now if I want to find the minimum of a function fxyz such that 2x plus 3y plus 4z, this is equal to 1. So this is the equation of the plane and this is the function, and we have to find the minimum of this function under this constraint. Clear? Now we know that absolute minimum of the function is at 0 0 0, and this point it doesn't satisfy this equation of the plane, because you are getting 0 plus 0 plus 0 is equal to 1, 0 is equal to 1. So Lagrange multiplier method will deal with such type of problems. That is, we have to find the extremum of the function fxyz such that the point it lies on some surface. So in this case, my surface is this plane. Clear? So geometrically, what is the meaning of this? That is, the point on the plane 2x plus 3y plus 4z is equal to 1, which is closest to the origin. So what is that one? Clear? So what will we do? We take any point xyz on the plane and then find the Euclidean distance of the point from the origin. So this is our function, which is square root of x square plus y square plus z square. Now we have to find the minimum of this function under this constraint. So it's an example of a constraint extremum problem. Clear? Now where we use the Lagrange multiplier, or what are the applications of Lagrange multiplier? So in industry, when we have to maximize the revenue under given budget, we use the concept of Lagrange multiplier. In economics, when we want to maximize utility function with fixed wealth constraints, we use the concept of Lagrange multipliers. Practical meaning of Lagrange multiplier method. So in this section, we present Lagrange method for maximizing or minimizing a general function fxyz subject to the constraint of the form gxyz is equal to k. So it's easier to explain the geometrical basis for the Lagrange multiplier method for the function of two variables. So what we did, we drawn the level curves for the equation fxy is equal to c, where c it varies from 7, 8, 9, 10 and 11. So for fxy is equal to c, I have this level curve, and then for fxy is equal to 8, I have this level curve, and this is for c is equal to 9, this is for c is equal to 10, this is for c is equal to 11. Now this is the curve corresponds to the constraints gxy is equal to k. Now at the point of intersection, the tangent of two curves are parallel. So the normals of two curves will also be parallel. This means at this point del f, this is equal to del of g, or you can say del f, this is equal to scalar multiple of del of g at this particular point of intersection. If I denote this point as x naught multipliers, to find the maximum and minimum values of the function fxyz subject to the constraint gxyz is equal to k. So the first step is find all values of x, y, z and lambda such that gradient of f is equal to lambda times gradient of gxyz is equal to k, which is the constant. Lambda is said to be the Lagrange multiplier. So we have to solve it, and on solving this we will get some points. Then you have to substitute those points in the given function. The largest of these values is the maximum value of f, and the smallest is the minimum value of f. So I have explained this step A by taking component wise of this vector equation. That will be in the more simpler form, that is explained in the next slide. Steps to solve Lagrange multiplier method. So in step we have del f is equal to lambda del g. So in component wise form this becomes fx is equal to lambda del gx, fy is equal to lambda times gy, fz is equal to lambda times gz, gxyz is equal to k. So it is a system of four equations in four unknowns x, y, z and lambda. So we will simultaneously solve these. So on solving this we will get the points, and on each point we will check the value of the function. That will give us the extremum value of the function. Now problems on Lagrange multipliers which you have to solve. First problem is a rectangular box without a lid is made up from 12 meters of cardboard. Find the maximum volume of such a box. Secondly, the plane xyz is equal to 1 cuts the cylinder x square plus y square is equal to 1 in an ellipse. Find the points on the ellipse that lies closest and farthest from the origin. So these two problems you have to solve. So in the next class we will discuss about double integrals in Cartesian and polar coordinates. Thank you.